Hello there, and welcome back to the Sleep Science. Tonight, above your head, stars scatter themselves across the velvet sky like spilled salt on black silk. Some of their light began its journey when mammoths still wandered ice fields, when humans first smeared handprints on cave walls. That same light, aged and persistent, is only now arriving at the back of your eyes. It's been through gravity wells, plasma storms, and billions of miles of silent nothingness. And you're just lying there, blinking at it like it didn't just survive cosmic battlefields to meet you. Honestly, you probably won't survive half of what a photon does in its first few seconds. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're awake enough to type, let me know where you're listening from and what time it is by you. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. It begins in a place you can't quite imagine, buried deep inside the core of a star, in a chamber of pressure so crushing that atoms surrender their structure and fuse together. Hydrogen becomes helium, and in that moment, just a few million degrees Kelvin, no big deal, a photon is born. Not one of those lazy photons you get from a light bulb. No, this is a gamma-ray photon, pure energy, sizzling with the fury of nuclear fusion. But here's the thing. That newborn photon doesn't just pop out of the star and streak toward Earth. Oh no, it's trapped, held hostage. It's surrounded by trillions of particles in a violent, boiling interior that makes rush hour traffic feel like spa music. Every time it tries to move, it crashes into another charged particle, scatters, ricochets, bounces, again and again, for tens of thousands, even millions of years. Yes, you heard that right. Some of the starlight you see tonight was born when humans were still chasing aurochs with sharpened sticks, but only recently escaped the star's surface. The distance from the star's core to its edge isn't so far, but the photon's path. It's like trying to walk straight across a stadium by bouncing off every person in every row. Historians still argue whether ancient civilizations understood this idea, even metaphorically, though early mythologies often hinted at a kind of divine slowness in starlight. As that photon bounces through the chaotic middle of the star, it gradually loses energy. It started out as a gamma ray, dangerous, blistering. But over time, as it stumbles through the layers of plasma, it gets reabsorbed, re-emitted, transformed. By the time it finally wriggles out of the star's outer layers, it might be visible light. Yellow perhaps like the sun, or blue-white if the star is younger and hotter, or maybe a deeper red if it's growing old and weary. And then it's free. There's no trumpet fanfare, no galactic cheer section. Just one lone photon tumbling into space at 299,792 kilometers per second. That's the speed of light, but in space terms. It's like sending a snail across a country. The nearest star to Earth other than the Sun is over 4 light-years away. That means even if a photon left Alpha Centauri right this second, it wouldn't reach us until the next US presidential election. No comment. But the silence of space doesn't slow the photon down. There's no air to bump into, no molecules to interfere. It's pure momentum now. The photon's just gliding. For years, centuries, millennia. If it were human, it would have gotten bored and taken up knitting by now. Along the way, it might pass a rogue planet drifting in the dark. It might skim the edge of a black hole's gravitational lens, bending just slightly like a whispered secret. It might get stretched by the expansion of the universe itself. This is what gives rise to redshift, by the way, which we'll get to later. But mostly, it just moves, quietly, unblinking, like a cosmic courier who doesn't sleep, doesn't age, doesn't even remember where it came from. One quirky, lesser-known theory once proposed that photons might age or tire out during their journey, losing energy over time, a concept called tired light. It was one of many attempts to explain why distant galaxies seem to be moving away from us. Turns out that theory didn't hold up, but it's a charming footnote in the story of how we try, again and again, to understand light. A bit like blamming your blurry photo on a tired camera lens. Eventually, one photon out of trillions strikes the atmosphere of Earth. Not all make it. Some are deflected, absorbed, scattered. Some become auroras over Norway. Some never even reach us, bouncing off space dust or satellites or unlucky weather balloons. But the lucky few punch through. If it's daytime, it'll blend into the sun's blinding wash. If it's night, and if you're lucky enough to be somewhere dark, somewhere quiet, maybe out camping or lying on a balcony, then you'll see it. Just one pinpoint, one glimmer, one tiny ancient message that says, "Hey, I made it." And that's the first starlight. Humans have looked up at it since before we had words for star. The ancient Babylonians tracked its movement. The Egyptians aligned pyramids to Sirius. Aboriginal Australian stories describe the Milky Way as a river or as a cosmic emu. We've always known it mattered, even if we had no idea how. Historians still argue whether early humans truly grasped the distances involved, or if stars were more like sky decorations to them. Either way, they watched, and so do you. You lie there now, your eyes half-lidded, your breathing slow. Somewhere in your retina, that photon meets a cell and triggers a tiny cascade of electricity, just enough to whisper to your brain, "Look." Not in words, not even in thoughts, just in wonder. You're not just stargazing. You're receiving ancient mail. And tomorrow, when you wake up and someone tells you stars are just balls of gas, you'll smile, because you know better. Stars are time machines. Stars are storytellers. And the light you see tonight, that's just the beginning of what they have to say. It's tempting to think of light as instant. Flip a switch, the room glows. But that's just local stuff. Starlight plays by cosmic rules. Out here in the quiet spaces between suns, distances are so laughably huge that we had to invent a new unit just to make the math hurt less: the light year. Let's get this out of the way first. A light year is not a measure of time. You'd think the name would help, but no, thank you, astronomy, for that little prank. A light year is a measure of distance, how far light travels in one Earth year. Spoiler alert, it's far. About 5.88 trillion miles or 9.46 trillion kilometers, give or take, because what's a trillion or two between stars? So when you hear that a star is 100 light years away, that means the light you're seeing right now left that star a century ago. A different world. Radios were new. Women in some countries still couldn't vote. The Titanic hadn't even made its dramatic iceberg debut. Yet that photon was already in flight, hurling itself toward a tiny blue dot that wouldn't notice it until tonight. This is why astronomy is essentially time travel for the extremely patient. Now here, where it gets deliciously weird. Let's say you look at a galaxy 2 million light years away. That means you're not seeing what it looks like now. You're seeing what it looked like when Homo habilis was figuring out how to use rocks without smashing their own feet. That galaxy might not even exist anymore. It could have been swallowed by a black hole, collided with a neighbor, or just burned itself out entirely. But we wouldn't know for another 2 million years. Historians still argue whether the ancient Greeks had any inkling of this delay. They certainly observed the heavens with precision. Ptolemy famously charted over 1,000 stars, but the idea that light travels at a finite speed, that came much later. Until the 17th century, many scientists assumed light's speed was infinite. Instant. Boom. There. It took the moons of Jupiter and the careful timing of their eclipses to prove otherwise. Enter Ole Romer, Danish, mustache, confused by why Jupiter's moon Io seemed to appear late when Earth was farther from Jupiter. Turns out it wasn't a scheduling issue. It was just the light taking longer to reach us. His 1676 estimate wasn't exact, but it was close enough to shake up physics. Suddenly, light had a speed, and with it came the dawning horror of just how far away everything really was. And once you understand that, something subtle shifts in your brain. You realize you're not just seeing stars, you're seeing ghosts. The sky becomes a museum of outdated exhibits. Some of the starlight hitting your eyes tonight comes from sources that no longer exist. You're watching a fireworks show where the fireworks burned out long before your invitation arrived. But this isn't a tragedy. If anything, it's romantic. Imagine a civilization on a planet orbiting a star 500 light-years away. If they had a telescope powerful enough and they pointed it at Earth, they'd be watching the Renaissance play out. Leonardo da Vinci sketching weird helicopters, Michelangelo painting ceilings, everyone wearing tights and taking astronomy very, very personally. It also means the universe has no real present moment. Everything is now, and everything is also long ago. When you look at Orion's belt, the leftmost star, Alnitak, is about 1,260 light-years away. The one on the right, Mintaka, only around 900. So even though they look like neighbors, the light from each began its journey at vastly different moments in our history. From your comfy position under a blanket or sprawled on the floor, you're watching multiple centuries unfold simultaneously. The sky has no chill. A fringe theory once suggested that if you could travel faster than light, you could see Earth's past by simply outrunning the light it emitted. Like, fly out 70 light-years at warp speed, turn around and watch Woodstock play out in real time through a cosmic telescope. Time travel, but with surveillance vibes. Charming, slightly terrifying, and also completely outside current physics. Still, someone's probably writing fan fiction about it. Back here in the real world, Starlight isn't just about pretty dots. It's a tool. It lets astronomers map the universe, estimate the age of celestial bodies, and even calculate the rate at which the cosmos is expanding. You've probably heard of redshift. That's when light from distant galaxies stretches toward the red end of the spectrum as they move away from us. It's one of the key pieces of evidence that the universe isn't static, it's growing. Which is mildly concerning, but also means your favorite stars are literally drifting into the past. We're part of that movement too. Our own sun's light takes just over 8 minutes to reach Earth. So in a technical sense, when you watch a sunrise, you're watching 8 minutes ago. Every selfie taken outdoors is slightly historical. You've never actually seen the sun in real time, and you never will. The moon, 1.3 seconds away, still a delay. That live feed from the Apollo missions, always slightly in the past. Even your Zoom calls bouncing signals off satellites are laced with lag. Time is stretchy, light is lazy, or just really committed to its pace, and nothing you see is truly now. Ancient cultures may not have had the math, but they got the vibe. The Inca, the Dogon, even Norse mythology, all featured cosmic time as cyclical or layered. The heavens weren't just above, they were beyond. And modern astronomy only proves them right in the weirdest possible ways. So tonight, when you glance up and spot Vega or Betelgeuse or any of the familiar starry companions, you're not seeing what they are. You're seeing what they were. The light has been traveling for so long, dodging comets and weaving through dust clouds, just to greet you here, on this exact night in this precise sliver of time when your eyes are open, and your brain is just sleepy enough to receive the message. You're not just stargazing. You're looking into a kaleidoscope made of centuries, stitched together with light. Time travel tourism, and the ticket was free. You've probably been lied to about stars. Not maliciously, of course, just gently misinformed by cartoons, holiday decorations, and the occasional over-enthusiastic planetarium volunteer. You've been told stars are white, that all starlight looks the same. But as you settle into the soft hum of the night, let your sleepy brain peel that myth apart. Because starlight is not white. In fact, it's a rainbow waiting to happen, just wildly stretched and hidden in plain sight. Every star sends out light across a spectrum of wavelengths. From energetic blues and ultraviolet to mellow reds and soothing infrared, each star glows with a unique blend of color, shaped by its temperature. Hotter stars, they burn blue or blue-white, radiating energy like they're late for something. Cooler stars, relatively speaking, settle into warm oranges or deep reds. And then there's our middle-aged sun, lounging in its pale yellow phase like a dad with socks and sandals. You don't usually see these differences clearly with your naked eye, though. Earth's atmosphere mutes things. That twinkle, it's not romantic. It's just atmospheric turbulence, basically space glitter getting punched by air currents. But through a telescope or with a nice long exposure phode, the universe blooms with color. Vega beams in icy blue. Betelgeuse, bless its wobbly heart, glows rust red. Rigel sparkles like the tip of a welding torch. This, by the way, is where it gets sneaky. If you take that rainbow light from a star and pass it through a prism or a diffraction grating, it spreads out into a stellar fingerprint. Astronomers call this a spectrum, and every little spike and dip in that band of color tells a story about elements, motion, pressure, and more. Here's the magic trick. Stars leave behind absorption lines, dark little notches in their spectrum where specific wavelengths are missing. Why? Because atoms in the star's outer layers are selfish. They absorb certain frequencies, leaving behind gaps, and those gaps match up with the known absorption lines of elements on Earth. It's like meeting someone at a party and recognizing them by the way they laugh. This is how we figured out that stars are made mostly of hydrogen and helium, without ever needing to touch them. Wild, right? You're lying there and your sleepy mind is decoding distant suns based purely on light squiggles. It's cosmic forensics, all from photons. The quirky bit, helium, the second most common element in the universe, was discovered in starlight before it was found on Earth. Back in 1868, astronomers studying the sun's spectrum noticed a strange yellow line that didn't match anything they knew. Must be a new element, they thought. And they were right. They named it after the Greek word for the sun, helios. It wasn't until years later that helium was isolated in earthly minerals. Imagine finding a new ingredient in your smoothie before it even exists in your kitchen. Historians still argue whether early spectroscopists understood just how groundbreaking this technique would become. At first, it was a novelty, a way to categorize stars by color, but very quickly it became the core method of stellar classification and the basis for so much of what we know about the universe today. That system, it's called the Harvard Spectral Classification, and it sorts stars by their surface temperature using a series of letters. O, B, A, F, G, K, M. Yes, the order is chaos. Yes, astronomers are still bad at naming things. There's a mnemonic for it. Oh, be a fine girl, guy, kiss me. But honestly, if you can remember that before bed, you deserve a gold star yourself. O-type stars are the hottest, fierce, blue, short-lived monsters. M-types are the coolest and dimmest, red dwarfs that hum gently for trillions of years. Our sun, right in the middle, a G-type main sequence star, steady, boring, life-sustaining. Think of it as the beige Toyota of stars, practical, dependable, and almost invisible among flashier cosmic rides. But here's the real sleepy miracle. Every star you've ever seen, every twinkle you've mistaken for magic, is singing its own silent, colorful song. You just need the right instrument to hear it. Spectroscopy is like giving stars a voice. One photon at a time, they tell you about fusion, gravity, age, chemical tantrums, and mood swings. They tell you if they're spinning fast or wobbling from unseen planets. They even whisper about magnetic storms that make our own sun look like it's having a mild caffeine buzz. There's also a fringe twist on all this. Some theorists once believed stars might be conscious in a way we can't yet measure, that their light signatures are coded signals or information packets. Not necessarily intelligence, but intention. It's speculative, sure, and not in any science textbook worth its salt. But still, the idea that every star might be sending more than just energy, a dreamy thought to fall asleep with. In the real world, the science stays grounded. Color and light shape our understanding of distance, age, composition, and evolution. It's how we know blue stars are young, burning through their fuel like rebellious teens, while red giants are elderly suns, puffed up with exhaustion and nearing their final acts. And when you lie back under that blanket of stars, squinting gently at the blue shimmer of Sirius or the orangey glow of Aldebaran, you're not just stargazing, you're color-grading the cosmos. You're seeing the moods of suns. The next time someone tells you stars are white, you'll just nod and smile, because you know they're not. They're blue, red, yellow, orange, violet, more vibrant than any paint palette. You just need the patience to let the light stretch out and tell its story. And lucky you, you've got all night. It's one thing to squint up at the stars and try to make sense of their shimmer with your naked eye, but at some point, humanity did what humanity always does. We built gadgets. Not just any gadgets, though. We crafted cosmic eyeballs, lenses to extend our vision beyond the reach of our squishy human eyes, telescopes, the original zoom and enhance for the universe. It all kicked off with a modest little cylinder and a very nosy Italian. In 1609, Galileo Galilei took a Dutch invention, a spyglass, and did what any overly ambitious nerd would do. He pointed it up. With a telescope barely stronger than your average pair of modern binoculars, he started something that would forever change how we see starlight. He didn't just spot new stars. He discovered that the moon had mountains, that Jupiter had its own mini-moon entourage, and that Venus goes through phases, like some sort of shy celestial influencer. Historians still argue whether Galileo fully grasped the implications of what he saw, but the church certainly had some strong opinions. It turns out, when your telescope reveals that Earth isn't the center of the universe, people get twitchy. Still, the race was on. Telescopes got bigger, bolder, and stranger. Some were housed in towers, others in remote mountaintops, all seeking clearer skies and less atmospheric interference. The rule was simple. The bigger the lens or mirror, the more light you can gather. And more light means seeing dimmer, farther, older things. It's like turning the brightness up on the universe itself. One particularly quirky chapter in telescope history involves William Herschel. This 18th century musician-turned-astronomer built a massive telescope in his backyard with the help of his equally brilliant sister, Caroline. Their scope discovered Uranus, not a bad achievement for what was essentially the world's fanciest garden hose. Herschel believed stars weren't just dots, but massive suns scattered across space, an idea still hotly debated at the time. Fast forward through centuries of glass grinding and mirror polishing, and suddenly we're launching telescopes into space. The game changer, Hubble. Deployed in 1990, the Hubble Space Telescope took Starlight to art gallery levels. With no atmosphere to blur its vision, Hubble revealed galaxies stacked behind galaxies, colorful nebulae twisting like spilled paint, and even gave us the Hubble Deep Field, the most mind-melting image ever taken. Just a patch of sky so small it looked empty. Until we stared into it long enough to see thousands of galaxies, each one full of stars, each one a time capsule. But even Hubble has its limits. Enter the new kid on the space block, the James Webb Space Telescope. Imagine a giant golden sunflower floating 1,000,000 miles from Earth, catching whispers of infrared starlight from the earliest galaxies. Webb's mirrors are so sensitive they can detect the heat of a bumblebee on the moon, though for the record, there are no bumblebees on the moon. Yet. Webb doesn't see stars the way you do. It doesn't collect light in your typical visual range. Instead, it sees the warmth of stars infrared. That means it can peek through dusty clouds, through the thick interstellar fog, into the star nurseries where baby suns are still swaddled in gas. It looks into the past, billions of years deep, and tells us what the universe looked like when galaxies were still awkward teenagers. Fringe idea for your dream bank. Some thinkers propose that starlight contains embedded patterns, more than just data about stars, but perhaps even coded messages from earlier civilizations. The telescope, in this view, becomes not just a tool, but a receiver. Again, no solid evidence, but the idea that looking at light might one day become listening to light. Let your dreams wander with that one. Back in the real, observable universe, telescopes have been getting clever. Not just bigger, but smarter. Adaptive optics now help ground-based telescopes wiggle their mirrors to counteract atmospheric distortion in real time. It's like giving your camera anti-shake for the whole sky. Suddenly, stars stop twinkling and start cooperating. There are also radio telescopes, massive dishes that collect wavelengths our eyes can't see. These scopes aren't looking at light as color but light as sound, sort of. In fact, the world's largest telescope array, ALMA, uses dozens of dishes scattered across the Atacama Desert in Chile to collect faint signals from the coldest places in the universe. Places where stars haven't even formed yet. Just clouds, just promises. Then there's the Very Large Telescope. Yes, that's its actual name. Astronomers are fantastic at math and tragically bad at naming things. But this Very Large Telescope, located in Chile, sees stars so clearly it can resolve individual features on nearby stellar surfaces. It's like staring into a lighthouse light and seeing the dust on the bulb. And all of it, all this gear, all this tech exists for one reason: to make sense of the starlight, because photons are stingy. You get a few, maybe a burst if a star flares, and that's it. No reruns, no second chances. You either catch the light or it slips past forever. That's the poetic cruelty of astronomy. You have to be ready and you have to look hard. And yet here you are, soft, sleepy, gazing upward from your blanket or couch or floor, part of a long lineage of star watchers. You may not be holding a telescope, but you're still tuned in. Your eyes, your imagination, your curiosity, they're little telescopes in their own right. Imperfect, yes. Atmospheric, definitely. But still, reaching. One day, our telescopes might peer far enough into starlight to glimpse the first flickers after the Big Bang. Or maybe the atmospheric signature of life on a distant exoplanet. Or a galaxy that's been hiding behind dust since before our solar system existed. But tonight, you don't need to solve the universe. You just need to see the light. Starlight doesn't just shine, it shifts. Imagine this: you're listening to a siren as an ambulance races toward you. The pitch rises, shrill and tense. Then it passes. Suddenly, the sound drops, stretching low as it disappears into the distance. That's the Doppler effect, and it doesn't just apply to sound. It happens with light too. That's right, starlight moves, not just through space but in space, and it tells us exactly how. When a star moves toward you, its light gets compressed, squeezed into shorter wavelengths. It shifts toward the blue end of the spectrum. We call this blue shift. And when it moves away, the opposite. The light stretches out, slows down, moves toward red. That's called redshift. It's subtle, infinitesimal even, but measurable. And astronomers have been obsessed with it ever since. The concept is simple, but the implications, astronomical, literally. Thanks to redshift, we know the universe is expanding, not standing still, not shrinking, growing. Space itself is stretching like warm dough in slow motion. Galaxies are drifting away from us, not because we're especially unpopular, but because the fabric of space between us is expanding. The farther away they are, the faster they seem to move. This is known as Hubble's law, and it's a cornerstone of modern cosmology. Historians still argue whether Edwin Hubble truly grasped the significance of his discovery in the 1920s, or whether it was just a neat little graph at first. Either way, it cracked open the cosmos. Suddenly, starlight wasn't just illumination, it was information, motion, history, and most exciting of all, mystery. But it gets juicier. Because stars don't move solo. They dance. They orbit. They fall in and out of gravity's grasp. And when two stars orbit each other in a close binary system, redshift and blueshift become tools to track their cosmic choreography. You can't see most binary stars as separate points of light. They're too close together, especially from Earth's perspective. But their light, it wiggles. One star swings toward us, blueshift. Then it swings away, redshift, like a galactic metronome. This subtle waltz allows astronomers to detect stars they can't directly see. In fact, it's how we first discovered black holes, not by spotting the black hole itself, but by watching the star it was dragging around. Its light shifted rhythmically, telling us something massive, but invisible, was nearby. Pretty much the creepiest way to discover anything. And it doesn't stop there. This same Doppler logic works for planets. When a star has a massive planet tugging on it, the star wobbles, not dramatically, but just enough for its light to shift slightly back and forth. That, called the radial velocity method, and it's one of the key ways we've detected exoplanets, worlds beyond our solar system, all from the way starlight subtly slides along the spectrum. There's something deeply satisfying about that. You're lying still, barely moving, and yet you're tapping into the motion of distant suns. Stars spinning, galaxies drifting, entire systems wobbling from the gravitational whispers of orbiting bodies. The cosmos is anything but static. Now there's a quirky debate you'll love. Some astronomers once pondered, what if light shifts not because of motion, but because of time itself? An early 20th century idea flirted with the notion that redshift could be due to the aging of light, something called tired light theory. The idea was that photons gradually lost energy over vast distances, like cosmic joggers getting winded. Charming theory, but it didn't fit with other observations, like time dilation in distant supernovae. Still, it's one of those, almost, theories that make you appreciate how weirdly precise our measurements have become. On a more grounded note, redshift has helped map the shape of the universe. We've charted galaxies and superclusters not just by where they are, but by how fast they're moving away. The result? A 3D cosmic map stretching across time, showing where matter clumps, where voids gape, and how structure emerges from stardust. Even the cosmic microwave background, the faint afterglow of the Big Bang, is bathed in redshift. That light, once a blistering white-hot blaze, has stretched into radio waves over 13.8 billion years. It's the ultimate redshifted glow, a whisper from the beginning of everything, still echoing across space. And yes, your sleepy brain can hold all that. Let's make it cozy. Imagine you're floating in space with a flashlight. You turn it on and gently start drifting backward. From someone else's view, the beam would stretch. The color would redden, drift fast enough, and your light could even shift out of the visible range entirely. That's what distant galaxies are doing, slipping into invisibility, one wavelength at a time. Even closer to home, Doppler effects are used in stellar weather forecasting. By watching the shift in spectral lines, scientists can detect starquakes, sunspots, even flares. Light not only tells you what a star is doing, but what it's about to do. Here's a fun fringe theory. Some thinkers wondered if extremely precise Doppler shifts could one day detect artificial movement, like the propulsion of alien spacecraft. If something were zipping between stars, bending the spectrum with deliberate speed changes, could we notice? So far, no suspicious signals. But it's a wonderfully paranoid bedtime thought, isn't it? For now, though, you can just rest in the knowledge that Starlight is honest. It won't lie about its motion. It may arrive late and a little tired, but when it gets here, it brings receipts. So as you lie back and look up, remember, every shimmer isn't just a pretty point. It's a GPS ping, a speed report, a whisper that says, "I'm moving," even if the shift is too subtle to see. The universe doesn't sit still, and neither does its light. Twinkle, twinkle, little star, yeah, about that. You've probably recited that 1,000 times, maybe to yourself, maybe to a small, squirmy human who refused to sleep. And sure, stars do twinkle, but not because they're trying to lull you into a gentle cosmic slumber. No, the real reason stars twinkle is far less magical and far more atmospheric. Let's start simple. Stars do not twinkle in space. If you were floating out beyond Earth's atmosphere, say on the International Space Station, or clinging gently to the hull of a research satellite, please don't. You'd notice something immediately. The stars look sharp, steady, crisp little dots frozen in place. No wiggling, no flickering, just silent, unwavering points of light. The twinkle, that's all us. It's a side effect of staring through Earth's squishy, unstable, perpetually moving air blanket. When starlight enters our atmosphere, it begins a chaotic obstacle course. The air above us is constantly in motion. Different temperatures, different pressures, different densities. Little pockets of air act like lenses, bending the incoming light this way and that. It's like trying to read a street sign through a swimming pool filled with invisible jellyfish that all have their own opinions. As a result, the light from a star jiggles slightly before it hits your eye. Sometimes it gets slightly brighter, sometimes dimmer. It shifts side to side. Your brain interprets this tiny dance as twinkling. Poetic, yes, but also deeply annoying to astronomers. Historians still argue whether early observers thought the twinkle was an inherent property of stars, or whether they simply accepted it as a charming mystery. Some even believed the twinkling meant the star was alive in some way. Ancient Chinese records described stars blinking during omens. Greek philosophers, ever poetic, linked twinkling to the imperfect sphere of fire in the heavens. Nice try, guys. But the reality is far less divine and far more turbulent. That same atmosphere that lets us breathe, fly planes, and complain about humidity is also the reason ground-based astronomy has limitations. You could build the biggest telescope on Earth, polish the mirror until it shines like your future, and it still won't solve the air problem. Your images will always have a touch of cosmic smear. That's why the world's top observatories are built in absurd places. Remote mountain tops, dry deserts, volcano summits. The idea is to get above as much atmosphere as possible. Less air equals less twinkle equals clearer starlight. Take Mauna Kea in Hawaii. It's a dormant volcano with some of the best atmospheric conditions on Earth. High elevation, low humidity, stable air. A telescope's dream. Or the Atacama Desert in Chile, bone dry, cloud-free, and totally inhospitable. If the stars had a fan club, these places would be VIP lounges. Still, even from the best spots, the air plays tricks. So astronomers got sneaky. They invented something called adaptive optics. Imagine a telescope mirror that shifts and wiggles hundreds of times per second to counteract the blur of the atmosphere in real time. It's like giving your telescope anxiety and then watching it become a perfectionist. The result? Stars that snap into focus like you've just wiped off foggy glasses. There's also lucky imaging. This is where you take thousands of short exposure photos and keep only the clearest ones, the rare moments when the atmosphere behaved. It's the astrophotography equivalent of only posting your best angles. Hey, even stars deserve to look good online. Of course, we eventually said, you know what? Let's just skip the atmosphere entirely. Hence space telescopes, Hubble, Webb, Spitzer. These orbital eyes float above the twinkle zone, collecting light in pure, uncorrupted streams. No atmospheric interference, just clean starlight straight from the source. But here's the twist. While astronomers hate twinkling, poets, painters, and small children adore it. There's something comforting about the tiny flicker of a star. It makes the sky feel alive. It reminds you that what you're seeing isn't a painting. It's a moving, breathing, reacting world beyond your own. And sometimes, atmospheric distortion gives us unintentional gifts. During rare conditions, stars can appear to shift color rapidly, red to green to blue in a kind of cosmic rave. Sirius, the brightest star in the night sky, is famous for this. People have mistaken it for UFOs. It's not aliens, just Earth's unstable breath playing pranks again. Here's a quirky historical tidbit. In the late 19th century, some sailors reported seeing flashing stars while at sea. They thought it was a maritime omen. Turns out, the combination of sea spray, low-angle starlight, and rapidly changing temperature layers created a kind of strobing effect. Sea stars, twinkling like disco balls. No portents, just physics. There's even a fringe theory, though mostly poetic, that suggests atmospheric twinkling might affect how we emotionally respond to starlight. That tiny shimmer could be triggering a subconscious signal of alive, making stars feel more personal, more sentient. Probably not scientifically sound, but if that helps you bond with Polaris on a lonely night, who's judging? So what does this mean for you? Sleepily blinking at a sky full of sparkles. It means the universe is stable, but your view of it is a little wobbly, and that's okay. The next time you see a star twinkling, Imagine the light traveling for hundreds or thousands of years, steady and unwavering, until the final few milliseconds of its journey, when it slips through 100 kilometers of fidgety atmosphere and takes on just the slightest shimmer. That last-second distortion is what you see. A star, filtered through air and gravity and temperature and time. It's like the universe is sending you a message, and the envelope got just a little crinkled on arrival. But still, it arrived. And that's the magic. You're drifting now, eyelids heavy, but stay with me, because it's time to read Starlight like a secret letter, not with your eyes, but with something far sneakier, something that turns light into language. That something is spectroscopy. It sounds intimidating, but it's really just the art of breaking down starlight into its ingredients, like reading a recipe without needing the kitchen. Every time light passes through a prism or a diffraction grating, it spreads into a rainbow. Not just the ROYGBIV you memorized in school, but a high-definition barcode of color, complete with telltale gaps and lines. And those lines, that's where the magic hides. Hear how it works. When atoms get excited, like when they're heated in a star, they emit light at very specific wavelengths. Think of each element like a musical instrument, only able to play certain notes. Hydrogen strums one pattern, sodium another. Helium does its own weird jazz solo. These patterns show up as emission lines, bright bands on an otherwise dark background. But in stars, something else happens. The outer layers of the star absorb some of the light before it escapes. So instead of bright lines, you get absorption lines, tiny dark slashes in the rainbow spectrum. And each of those slashes is a signature, a cosmic fingerprint. You match the line to the element and boom, you know exactly what the star is made of, without ever touching it. This was the scientific version of witchcraft back in the 1800s. Two scientists, Kirchhoff and Bunsen, yes, that Bunsen, the one with the burner, were the first to systematically match these spectral lines with elements. Suddenly, starlight wasn't just a glow, it was a code, a whisper of chemistry from across space. Historians still argue whether early astronomers grasped just how powerful this tool would become. Spectroscopy didn't just open a window, it tore down the wall. Overnight, astronomy became astrochemistry. Stars went from mysterious pinpricks to analyzable laboratories. You could tell their temperature, their velocity, even their age, just from those tiny spectral hiccups. Let's get a bit dreamy here. The first time someone pointed a spectroscope at a star and saw that barcode of light, that must have felt like translating alien poetry. A language no one had ever heard, suddenly revealing itself, one photon at a time. Of course, this didn't just stop with stars. Spectroscopy let us analyze nebulae, galaxies, even distant exoplanet atmospheres. When starlight filters through a planet's clouds, some of it gets absorbed by molecules in that atmosphere. The result? A unique absorption pattern. Astronomers can now detect water vapor, methane, and even hints of possible biosignatures just by watching a planet eclipse its star and catching the light that filters through. In other words, we can smell planets with starlight. Take that in for a moment. You are lying in the dark, while people on a rocky sphere 93 million miles from its star are sniffing the skis of planets light years away. And it works because of lines in a rainbow. Here's a quirky detail. Some spectral lines are so consistent, so precise, that we use them as cosmic rulers. The hydrogen alpha line in particular is like a yardstick for galaxies. If that line appears redshifted, you know the object is moving away. If it's blue-shifted, it's coming toward us. Spectroscopy doesn't just reveal what something is, it tells us what it's doing. But things aren't always that clear. There's a special kind of star that throws a wrench into the works, chemically peculiar stars. Yes, that's their real name. These divas of the stellar world show bizarre spectra. Elements like silicon, mercury, or even rare earth metals show up in odd concentrations. Why? Still not fully known. Historians and astrophysicists still argue whether these anomalies are due to magnetic fields, stellar winds, or just cosmic drama. Some stars even flip their entire spectrum over time. Variable stars like Myra shift their chemical signatures as they pulse. Imagine a campfire that changes its smoke scent every few hours. Stars that reinvent themselves. How very on brand for the universe. And then there's the tale of the Fraunhofer lines. These dark absorption lines were first observed in the early 1800s by Joseph von Fraunhofer, who wasn't even trying to decode stars. He just wanted better glass for telescopes. Instead, he found hundreds of fine dark lines crossing the sun's spectrum. We didn't even know what they meant yet, but there they were, cosmic fingerprints already waiting. Turns out those lines are mostly caused by the sun's own atmosphere absorbing specific wavelengths of light. But some come from Earth's atmosphere. That's right, your sky leaves smudges on the light from other stars. Even when we study the cosmos, we can't help but leave fingerprints on the lens. Fringe theory time. A few researchers once speculated whether we could use this spectral trick in reverse, broadcasting ultra-specific laser patterns into space to attract attention from intelligent life. Basically, sending out our own barcodes in the hope someone's spectroscope is watching. So far, no response. But who knows? Maybe our signal just hasn't arrived yet. Back in your cozy bed or tucked in sleeping bag, none of this seems urgent. You don't need to build a spectroscope. You don't need to name a spectral line or memorize helium's emission pattern. But it's oddly comforting to know it's all out there. Every star above you isn't just burning, it's talking, softly in frequencies and lines, telling you what it's made of, where it's been, what it might become. Starlight doesn't just shine, it says something. And you, dear sleeper, are part of the only species we know that can listen. So close your eyes if they aren't already and picture a thin rainbow sliced by dark threads, a barcode glowing in space, a secret message, half sung, carried across time. The stars aren't just shining for you. They're telling you their story. You're already floating through space in your mind, might as well check into a hotel. But not just any hotel. This one doesn't have bellhops or chocolates on the pillow. It's the Hertzsprung Russell diagram, the most oddly glamorous chart in the entire universe. No, seriously, it's a graph. A pretty simple one, really, just temperature on one axis, brightness on the other. But on this humble grid, you can find the past, present, and future of almost every star that's ever existed. And yes, you're about to become the kind of sleepy genius who understands stellar evolution. The HR diagram was born in the early 1900s when two astronomers, Ejnar Hertzsprung and Henry Norris Russell, were trying to make sense of all this starlight data people were collecting. Historians still argue whether they intended to create a cosmic life chart, or if it was just a convenient way to compare temperatures and luminosities. Either way, it turned into a stellar family photo, frozen in time. Here's the basic layout. Across the bottom of the chart is temperature, but because astronomy likes to keep things spicy, it's reversed. Hotter stars are on the left, cooler ones on the right. The vertical axis shows luminosity, or how bright a star is compared to the sun. The farther up the graph, the more the star is basically shouting, "Look at me," into the void. Most stars, including our sun, fall along a long, swooping line called the main sequence. Think of it as the cosmic middle class. These stars are steadily burning hydrogen in their cores, living stable, responsible lives. Some are big and bright, others small and dim. But they're all following the same rule. More mass means more fuel, and more fuel means hotter, brighter, and, unfortunately, shorter lifespans. A small red dwarf might burn for trillions of years. A massive blue O-type star, maybe a few million. It's like comparing a tea candle to a fireworks finale. Same process, just wildly different packing. Then you have the giants and supergiants up in the top right corner. These are stars nearing the end of their lives, swollen, unstable, bloated with leftover helium and heavier elements. Their temperature might not be extreme, but their sheer size makes them absurdly bright. Betelgeuse, for example, is a red supergiant. If you replaced our sun with Betelgeuse, its surface would swallow everything out to Jupiter. No big deal. Down in the bottom left, that's where things get weird. Welcome to the white dwarfs, small, dense remnants of stars that used to be like our sun, no longer fusing anything, just glowing faintly with leftover heat. If the HR diagram had a basement, these guys would be hiding down there in thick cardigans, muttering about the good old days. Here's the beauty of it. Just by knowing a star's temperature and luminosity, often gleaned from its color and spectrum, you can slap it onto this diagram and know what kind of life it's living. Are we talking youthful energy, midlife stability, elderly chaos, a faint whisper of memory? It's all here. The HR diagram even lets us map the path stars take over their lifetimes. It's not static, it's a storyboard. A star is born, usually in the main sequence. As it burns through its hydrogen, it shifts, it swells, it climbs up into the red giant phase. Then, depending on its mass, it either shrinks into a white dwarf or goes full drama and explodes in a supernova. Astronomers call these paths evolutionary tracks, and yes, they're as dramatic as they sound. Some stars zigzag through the diagram in chaotic bursts. Others coast gently along predictable curves. Some end up in places we don't quite expect. Looking at you, blue stragglers. How are you still burning that hot? Suspicious. Fringe theory time. There's been speculation about hypothetical stars that would fall off the diagram entirely, objects like quark stars or preon stars. These would be denser than neutron stars, maybe colder, maybe invisible to typical observation. If they exist, they'd be lurking somewhere outside the HR framework like cosmic cryptids. No solid evidence yet, but the HR diagram might not be the final word. Meanwhile, back in normal space, we use this diagram like a cosmic guest book. Clusters of stars, like the Pleiades or the Hyades, are especially fun. Since all the stars in a cluster are born at roughly the same time, comparing their positions on the HR diagram reveals their collective age. The more massive stars evolve off the main sequence first. So, by spotting where the turn-off point is, you can estimate how long they've been burning. It's like carbon dating, but sparkly. And guess what? You can even spot imposters this way. If a star is brighter than expected for its temperature, it might be part of a binary system where two stars are blending their light. Or maybe it's surrounded by a disk of dust. Or it could be variable, changing in brightness over time. The HR diagram lets you flag these oddballs, the ones who don't fit the neat narrative. There's a certain sleepy peace in this. You lie back, stars blinking overhead, and you realize that somewhere quietly, there's a chart that describes it all. Not just where a star is, but where it's going. It's Starlight with a storyline. One day, long after you and I are gone, the sun will leave the main sequence. It'll puff up, shed its outer layers, and settle into white dwarfhood. It's not tragic, it's transformation. Every point on the HR diagram is a phase, a purpose, a role in the longest-running drama the universe has ever staged. So now when you see a blue-white spark on the horizon, you'll know hot, young, reckless, a red glower, elderly, bloated, reflective, a dim, steady glow, someone who's done their work and now just hums quietly to themselves. The diagram is still there, waiting. And tonight, so are you, tucked into the long arc of a stellar story, watching from your temporary twinkling seat. Not all stars are consistent. Some pulse, some dim, some explode, and some behave like emotional teenagers, bright one moment, collapsing into themselves the next, throwing fits of light and fury for reasons we only half understand. Welcome to the world of variable stars. While most stars keep their brightness relatively steady over time, those stable, responsible types we met back on the Hertzsprung-Russell diagram, variable stars are a whole different category. Their luminosity shifts, sometimes predictably, sometimes chaotically, sometimes for physical reasons, sometimes for reasons that keep astronomers awake at night. Let's start with the easy ones, pulsating variables. These stars literally expand and contract over time, their surfaces swelling and shrinking like slowly beating hearts. As they do, their brightness changes. One famous group of these is the Cepheid variables. They're like the metronomes of the universe. Their periods, the time it takes them to pulse, are tightly linked to their luminosity. The longer the cycle, the brighter the star. That simple rule, discovered by Henrietta Swan Leavitt in the early 1900s, revolutionized astronomy. Historians still argue whether she received proper credit. Spoiler, she didn't, but her work laid the groundwork for measuring cosmic distances. Find a Cepheid, measure its pulse, calculate its actual brightness, and then compare that to how bright it looks. The difference tells you how far away it is. And just like that, Starlight became a yardstick. But not all variables are so well behaved. Some stars vary in brightness because of eclipses, what we call eclipsing binaries. Two stars orbiting each other, and from our vantage point, one regularly passes in front of the other. The light dims, then brightens again, like watching a flashlight get covered by a slow-moving thumb. Algol in the constellation Perseus is the classic example. Ancient observers even called it the demon star because of its unsettling flickering. Then there are eruptive variables, stars that spit out sudden flares of energy, mass ejections, sunspots, magnetic tantrums. These bursts are less rhythmic, more violent. Think of them like stellar sneezes. Unpredictable, often explosive, occasionally blinding. And some of these tantrums, we still don't understand them. Take the star KIC 8,462,852, better known by its internet alias, Tabby's star. Discovered in 2015, this seemingly normal star started showing weird, erratic dips in brightness, up to 22%, which is huge. It wasn't periodic. It wasn't symmetrical. It wasn't like anything we'd seen before. Cue the conspiracy theories. Some suggested dust clouds. Others proposed comet swarms. And yes, a few people floated the idea of an alien megastructure, like a Dyson sphere under construction. While there's no solid evidence for that, the truth is, we still don't know for sure. Tabby's star continues to whisper strange light patterns into our telescopes, daring us to figure it out. Here's a quirky, lesser-known detail. Some stars vary because they're rotating. If a star has a big spot on its surface, a cooler, darker patch, it'll look dimmer when that side's facing us. Then it rotates and we get the bright side again. It's a cosmic lazy Susan. These rotating variables help us study star spots, magnetic fields, and how a star's outer layers behave over time. There are even cataclysmic variables which live up to their dramatic name. These are binary systems where one star, usually a white dwarf, is pulling material off its companion. The stolen gas builds up on the surface until, boom, you get a sudden bright outburst. Not quite a supernova, but not a polite glow-up either. Speaking of supernovae, we'll get to those fireworks in the next section. For now, just know that the universe saves its most violent light shows for last. But variable stars aren't just troublemakers. They're teachers. Every flicker is data. Every shift in brightness tells us something about a star's internal structure, its layers, its density, even its core dynamics. We can't crack them open, but we can listen to their heartbeat. There's an entire field called asteroseismology, where scientists study the oscillations inside stars. Yes, stars have seismic activity, just like Earth. Pressure waves ripple through their interiors, and these vibrations subtly affect their light. By analyzing those changes, astronomers can create detailed models of how stars are built. It's like performing an ultrasound on a sun. Some variable stars are also extremely old. RR Lyrae variables, for example, are found in globular clusters, those dense, spherical star cities that orbit galaxies. These stars are ancient, billions of years old. They've been pulsing longer than Earth has had continents, and their regular flickering gives us clues about the age and shape of the Milky Way itself. Now let's zoom way out. If you observe an entire galaxy and see a supernova flare or a Cepheid blink from inside it, you're not just watching a star, you're reading that galaxy's timeline. One tiny flicker can recalibrate our whole understanding of space. Which brings us to a fringe but delightful debate. Could variable stars be used as communication? Like, what if some distant civilization modulated a star's brightness on purpose, encoding signals in the pulse? It's the long-range version of Morse code across light years. While we've seen no evidence of this, the idea persists in the sci-fi corners of astrophysics. The night sky as a cosmic radio station, broadcasting on frequencies of flicker. But tonight, for you, it's simpler. You're lying under a sky full of blinking stars, and now you know it's not just your eyes. It's not just the atmosphere. Some stars really are flickering. Some really are pulsing. Some might be sending out flares or shrinking and swelling in a rhythm older than history. You don't need to measure it. You just need to notice. And now that you've noticed, you'll never see a star the same way again. What looked like stillness is full of breath. What looked like silence is full of song. Now remember those polite little variable stars from before, the ones that pulse and wobble and occasionally throw a gentle tantrum. Lovely creatures. But tonight, you're going to meet their much louder, much more dramatic cousins. These are the stars that explode. No poetic metaphor, no gentle fade to black. These are literal cosmic detonations. Because sometimes when stars die, they don't go quietly into that good night. They go full-blown supernova. Let's set the scene. A massive star, many times bigger than our sun, has been living its best hydrogen-fusing life for millions of years. Burning hot, burning fast. At first, it fuses hydrogen into helium in the core. Once the hydrogen runs out, no problem, it starts fusing helium into carbon, then carbon into oxygen, then into neon, then magnesium, then silicon. Each new element takes more and more effort to fuse, until finally, iron. And this is where the universe draws the line. Iron doesn't release energy when it fuses, it absorbs it. So when the star's core becomes mostly iron, fusion grinds to a halt. There's no more outward pressure to fight gravity. The core collapses in a fraction of a second. The outer layers fall inward, temperatures skyrocket, and then boom. A Type II supernova is born. We're talking about an explosion so powerful it outshines entire galaxies for days or weeks. The starlight you see, that's just the outer debris being thrown off at unimaginable speeds. The real drama happens at the center, where the collapsing core either compresses into a neutron star, a city-sized ball of ultra-dense matter, or if it's massive enough, collapses into a black hole. Light can't even escape that. Talk about an exit. Historians still argue whether ancient civilizations ever saw and understood supernovae. But there are clues. Chinese astronomers recorded a guest star in 1054 AD that was visible even in daylight for weeks. That wasn't a planet or comet. That was a supernova. Its remnants still haunt the sky today as the Crab Nebula, a tangled web of gas and dust slowly unraveling in silence. Some Native American petroglyphs are thought to depict this same event, carvings of exploding stars etched into stone. Even without telescopes or spectral analysis, people noticed. Because when a star explodes, you don't miss it. But not all supernovae are the same. There's another flavor, Type Ia. These don't come from massive stars. Instead, they're caused by white dwarfs, those hot, dense stellar leftovers we met a few sections ago. If a white dwarf is orbiting a companion star, it can slowly steal material from its partner. If it gets greedy and crosses a certain mass threshold, about 1.4 times the mass of the Sun, it can no longer hold itself together. And kaboom, no slow collapse, just instant obliteration. These are some of the brightest explosions in the universe, and they happen in galaxies full of old, dim stars. We love them, though, because they always explode at about the same brightness. That makes them perfect standard candles for measuring distance. It's like spotting a 100-watt bulb across the universe. You can tell how far it is by how dim it looks. Type Ia supernovae have literally helped us measure the expansion of the cosmos. And yeah, that expansion, it's accelerating. That's how we discovered dark energy, by watching the light from these dying stars. So basically, the universe is being pushed apart by a force we don't understand, and we only know that because some white dwarf got too clingy with its neighbor and exploded. Thanks, stellar drama. Quirky side note, there are also superluminous supernovae, giants among giants, hundreds of times brighter than typical explosions. We're still trying to figure out how these happen. Magnetars, collapsing parent stability stars, aliens with a taste for fireworks. Too soon to say. But they glow like galactic lighthouses, and if you saw one in our sky, you'd probably mistake it for a second sun, or go temporarily blind. Either way, memorable. There's even a rare class of failed supernovae, where the star collapses directly into a black hole with almost no light at all. A disappearing act. One moment, a star is there. The next, gone. Observatories track these events like ghost hunters, looking for stars that vanish without a trace. Imagine that. A star lives for millions of years, shining across galaxies, and its final moment is complete silence. Now here, where you, sleepy stargazer, get a front row seat. Because when these stars go nova, their light can travel for thousands or millions of years before it reaches us. That means a supernova you see tonight might have happened during the Roman Empire, or the Bronze Age, or while trilobites were still the coolest thing crawling around. It's time-lapse tragedy, delayed fireworks. And you don't have to go far to see a future example. Betelgeuse, the red supergiant in Orion's shoulder, is a prime candidate for a nearby supernova. It's bloated, unstable, and acting weird. In 2019 and 2020, it dimmed dramatically for weeks, sparking rumors it was about to blow. Not yet, but someday, maybe tomorrow, maybe 100,000 years from now, it will explode. And when it does, it'll be visible in daylight, for weeks. You'll be able to read a book by Starlight. Don't worry, it's far enough away that we'll be fine. No earth-shattering kabooms. Just a free light show and an existential reminder that even the brightest things burn out. Fringe speculation. Some theorists wonder if ancient mass extinctions on Earth might be linked to nearby supernovae. A close enough blast could strip away the ozone layer, bombarding the surface with radiation. No definitive evidence yet, but the idea is definitely explosive. So as you lie there, head turned lazily toward the sky, remember, not every star dies quietly. Some go out in glory, in brilliance, in raw, uncaring violence. And their light, fleeting, furious, travels across the void for eons just to brush across your eyelid. You might blink, but it took millions of years to arrive. Not all stars dance alone. Some find a partner, lock into an eternal gravitational embrace, and whirl around each other for billions of years. These are binary stars, and they're more common than you might think. In fact, most stars in our galaxy, maybe even 2/3 of them, are in some kind of binary or multi-star system. Our sun is actually the oddball, a lonely bachelor in a galaxy full of couples. But these stellar relationships aren't always romantic. Sometimes they're codependent, sometimes they're chaotic, and sometimes, especially in the case of close binaries, they're downright toxic. Let's start with the basics. A binary star system is simply two stars orbiting a common center of mass, called the barycenter. Sometimes both stars are visible. They swing around each other like Olympic figure skaters, graceful and obvious. We call these visual binaries. Other times, we only see one star. The other might be too dim or too close to be resolved, but we can still detect its presence, usually by watching the primary star's light shift. Remember our friend the Doppler effect. If a star wobbles ever so slightly, its spectral lines shift back and forth. That's the telltale sign of an astrometric binary. Then there are the dramatic ones, eclipsing binaries. These systems are perfectly aligned from our vantage point, so one star passes in front of the other at regular intervals. The result? The total brightness dips like a heartbeat on a monitor, then it rises again. These stars don't just orbit, they block each other's light in a perfect rhythm. One famous example is Algol, also known as the demon star. To the naked eye, it seems to dim and brighten every few days. Ancient people noticed. They didn't know why, but it felt ominous. Turns out, Algol is an eclipsing binary with a larger but dimmer companion crossing in front of the brighter star every 2.86 days. No demons, just gravity doing its thing. Historians still argue whether early civilizations truly documented binary stars, or if those records were poetic interpretations of these brightness changes. But once telescopes and spectroscopy came into play, the double star dance became undeniable. Here where it gets spicy. In close binary systems, the stars are so near each other that their gravitational fields overlap, and in some cases, the larger star steals material from its companion. This is called mass transfer, and it's as dramatic as it sounds. Gas spirals from one star to the other, forming an accretion disk, a glowing halo of stolen matter slowly being devoured. If the receiving star is a white dwarf, you might get periodic outbursts of energy, like a nova, a temporary brightening caused by runaway nuclear fusion on the surface. Not quite the all-out explosion of a supernova, but still pretty spectacular. It's like borrowing too much sugar from your neighbor and accidentally blowing up the kitchen. Even more extreme, when one of the partners is a neutron star or black hole. In these cases, the accretion disk becomes a furious, swirling nightmare, heating up to millions of degrees and emitting intense X-rays. These are the X-ray binaries, and they're some of the brightest high-energy sources in the sky. Let that settle for a second. Somewhere out there, two stars are locked in a death spiral. One is literally eating the other alive, and the light from that cosmic cannibalism is shining in your general direction. Sleep tight. But not all binaries are so aggressive. Some just quietly orbit, influencing each other's evolution. A more massive star will age faster, leaving behind a white dwarf while its smaller partner continues to burn steadily. Some pairs might even merge, slowly spiraling in until they collide. That collision can trigger gravitational waves, those ripples in spacetime first detected in 2015. Fringe theory moment. A few researchers have proposed that some of the universe's more bizarre events, like gamma-ray bursts or fast radio bursts, could come from the collision of compact binary stars. Neutron star merges, white dwarf smashes. It's stellar bumper cars at relativistic speeds. Sometimes these mergers leave behind weird things. An unusually massive neutron star, a hypernova, or maybe just a rapidly spinning stellar corpse flinging energy into space. And you, back here on Earth, might detect that moment in a spike of starlight, or in a ping of gravitational waves, like hearing the faint thud of a door closing in a house across the universe. Astronomers are obsessed with binary systems because they help answer big questions. How do stars evolve under pressure? What happens when gravity gets too clingy? Where do black holes come from? How do we detect planets in chaotic multi-star environments? Yes, there are planets that orbit binary stars like little cosmic third wheels. These are called circumbinary planets, and they have two suns in their sky, just like Tatooine in Star Wars. And they're very real. Kepler 16b was the first confirmed one. Can you imagine a double sunset every night? Good luck scheduling a beach party. There's even speculation that some rogue planets, the loners drifting through space without a star, were ejected from unstable multi-star systems, born into chaos, kicked out for good. But back to you. You're lying there, one eye open, scanning the constellations, and somewhere in that twinkle is a duet, two stars locked in orbit circling each other for eons. Their combined light reaches you as a single point, but behind that glow is a ballet, tidal pulls, magnetic storms, maybe even a long, slow spiral into oblivion. From here it's peaceful, just light, but out there, It's the quiet tension of a relationship built on fusion, gravity, and time. Binary stars remind you that light isn't always solo. Sometimes it comes in pairs. Sometimes it's complicated. You'd think light would behave itself. After all, it's just a stream of photons barreling through space in a straight line at the speed of, well, light. No swerving, no detours, just a nice clean path from source to eyeball. But no, light can't just leave it at that. Because gravity, as always, has other plans. Welcome to the strange and wonderful phenomenon of gravitational lensing, where space itself becomes a warped, magnifying window, and starlight takes a detour around massive objects like galaxies, clusters, and the occasional black hole. It's the cosmic equivalent of looking through the bottom of a wine glass and seeing the universe all bent out of shape. Hear how it works. Einstein's general theory of relativity tells us that massive objects, like stars, galaxies, or even dark matter, warp the fabric of space around them. And when light passes near that warped space, it bends. Not because the light wants to bend, but because space itself is curved, and light always takes the shortest path through it, even if that straight line is now a big cosmic swoop. This bending of light is gravitational lensing, and it's not just a curiosity, it's a tool. When a distant star or galaxy lines up just right behind a closer, massive object, the light gets distorted. Sometimes it appears brighter, sometimes it forms arcs or rings. Occasionally, it splits into multiple images of the same object, like a cosmic funhouse mirror. The most famous of these illusions is the Einstein ring, a perfect circle of light formed when everything aligns just right. Background object, foreground lens, and you. It's rare, delicate, and wildly beautiful. A full ring of starlight bent by gravity, glowing like a luminous halo in space. Historians still argue whether Einstein predicted the full implications of this when he first scribbled out general relativity in 1915. He knew light would bend, sure, but did he imagine galaxies being magnified and twisted into floral spirals by clusters of dark matter? Probably not, but his equations left the door wide open. The first real proof came in 1919 during a solar eclipse. British astronomer Arthur Eddington measured the position of stars near the sun's edge and found them shifted, just slightly, from where they should be. Their light had been bent by the sun's gravity, a barely there nudge, but enough to confirm Einstein's theory and send the physics world into a frenzy. Fast forward a century, and we're using gravitational lensing to do way more than win science bets. Now we use it to detect galaxies too faint or too distant to see otherwise. When a massive galaxy cluster sits in front of a deep field of space, it acts like a natural telescope, magnifying the light of objects behind it. This is called strong lensing, and it lets us see things from the early universe, baby galaxies, less than 1 billion years old, whose light would otherwise be swallowed by distance. You're basically using gravity as your lens. And then there's weak lensing. This one's subtler. No flashy rings or arcs, just a statistical smearing of background galaxies caused by large-scale distributions of dark matter. It's one of the only ways we can see dark matter at all, by watching how it bends light from things behind it. It's like tracing the shape of an invisible mountain by how the wind flows around it. Fringe theory sidebar. Some researchers have speculated about microlensing caused by rogue planets or even hypothetical alien megastructures. When a small object passes in front of a background star, it can momentarily brighten the star's light, not from reflection, but from gravity bending the light toward us. We've actually used microlensing to find exoplanets this way, without ever seeing the planets themselves. Just a tiny flicker in a distant star's brightness. The faintest ripple of gravity, and we catch it. And then, of course, there's the grand spectacle, black holes. Nothing warps space more dramatically. If a star passes behind a black hole, its light can be bent so sharply that you might see it on both sides of the black hole at once. Its light curves around the void, showing you the stars front and back simultaneously. Talk about an overachiever. Some of the most surreal gravitational lensing images come from black holes. In simulations, and now in real telescope data, you see rings, crescents, and warped reflections that don't quite make sense. That's because your brain is trying to interpret 3D spacetime bending in ways it wasn't built for. It's like trying to fold a paper crane from a Möbius strip. Astronomers even use lensing to look for primordial black holes, tiny theoretical leftovers from the early universe. If they exist, their gravity would occasionally cause microlensing events in stars. So far, nothing conclusive, but the search continues. Here's the dreamy part. Gravitational lensing means that light doesn't just travel, it paints. It traces curves around gravity wells, like a dancer spiraling down invisible stairs. It shows you the same galaxy from 3 different angles. It magnifies the tiniest flickers from across time. So tonight, as you lie still under a sky of steady stars, remember, some of that light didn't travel in a line. Some of it bent, curved, detoured around massive objects you'll never see. Some of the photons that reached your eyes took a longer path, not out of confusion, but because space itself told them to. And yet they got here. Gravitational lensing reminds you that the universe isn't flat. It's lumpy, wobbly, warped by mass and time. Light doesn't always take the easy road, but it finds a way. And sometimes, when the alignment is just right, gravity itself becomes a telescope. And you, half asleep in the quiet dark, get to witness the universe not as it is, but as it bends. You're going to need to hush your thoughts now, because we're entering one of the quietest corners of the cosmos. A nursery, not for bobbies, for stars. These are stellar nurseries, vast, cool, dark clouds of gas and dust scattered throughout galaxies. And despite being where stars are born, they don't look like much at first. Not to the naked eye anyway. More like smudges or shadows in space. But inside, they're glowing with the promise of light. They just haven't let it out yet. Here, deep in the murky heart of a molecular cloud, gravity begins its slow, irresistible pull. A random patch of gas, mostly hydrogen, starts to clump together. Not because it's in a rush, but because it can't help itself. One hydrogen atom bumps another, then 100, then 1,000, then millions. And the more they clump, the more gravity pulls them tighter. Eventually, the core gets dense enough and hot enough for something miraculous to happen. Hydrogen atoms fuse. Light is born. A star takes its first breath, not with sound, but with heat and photons. This early star is called a protostar, and it's still wrapped in its dusty cocoon. The light it emits can't get far in the visible spectrum. That's why, when we look at star-forming regions, we don't use ordinary telescopes. We use infrared. Because while visible light gets blocked by all that gas and dust, infrared light slips through like a whisper. Gentle, persistent, warm. That's how the James Webb Space Telescope peeks into these nurseries. Its infrared vision reveals structures previously hidden. Knots of collapsing gas, baby stars huddled together, jets of material blasting outward like stellar hiccups. It's like switching on a flashlight under a blanket and suddenly seeing a whole world you didn't know was there. Take the pillars of creation, for example. You've probably seen them, a hauntingly beautiful image of tall, dusty columns in the Eagle Nebula. Hubble first showed them to the world in visible light, majestic, cloudy towers. But Webb saw right through the dust, revealed the glittering infant stars inside. Stars you can't see with your eyes, but that are already burning with their own tiny nuclear fires. Historians still argue whether early astronomers understood that stars formed, that they weren't always just there. But ancient cultures certainly revered nebulae. The Chinese called some of them cloudy stars. Indigenous Australians had stories about the Coalsack Nebula, describing it as a celestial emu's body. Even if they didn't see the stars within, they saw the mystery of these dark patches. The science caught up slowly. Today, we know star formation is a chaotic, inefficient process. Most of the gas in these clouds doesn't become stars. Some parts collapse. Others are blown away by the radiation from nearby massive stars. Sometimes, newborn stars emit jets of material, powerful outflows of charged particles that clear away the surrounding gas. It's as if the baby star is saying, "I need space." Quite literally. These jets carve out cavities in the nebula, allowing some light to escape. Over time, these stars will fully emerge from their cocoons. They'll ignite properly, enter the main sequence, start living their long, slow lives of fusion and flare. But while they're still young, they're shrouded, glowing but hidden, like fireflies trapped in smoke. Some nurseries become so packed with newborn stars that they glow from within. That's how we get HII regions, ionized hydrogen gas lit up by ultraviolet light from the brightest, hottest stars. Think of them as neon signs in space. The Orion Nebula is a classic example, a swirl of color, light, and baby stars caught mid-blink. And yes, the Milky Way is littered with these birthplaces. Most are tucked along the spiral arms of our galaxy, where gas is most plentiful. It's a slow but steady cycle. Gas forms stars, stars live and die, their remains enrich the gas, and the next generation begins. There's even evidence of triggered star formation. Imagine a massive star goes supernova near a gas cloud. The resulting shockwave compresses parts of the cloud, kick-starting new collapses. One star's death literally creates the conditions for dozens more to be born, a cosmic cycle of sacrifice and renewal. Fringe speculation alert. Some theorists wonder whether early galaxies formed stars differently, faster, more chaotically, maybe even forming massive stars we'd never see today. The so-called population III stars, thought to be made of pure hydrogen and helium, might have burned hot and lived fast. We've never observed one directly, but Webb is on the hunt. If we ever catch that light, ancient, exhausted, it could change everything we know about the first starlight. Back here in the present, you just need to close your eyes and imagine. A black patch of sky, silent, still. Then inside that darkness, motion, pressure, heat. Invisible flickers of infrared light. Tiny suns flicking on, one after another like matches in the void. Not chaos, not noise, just birth. And the light they emit tonight, it might take 1,000,000 years to break through the dust, to escape the cloud, to find its way here to your retina. You won't be around to see it. But it's coming. Every starlit sky is full of these promises. Stars not yet visible, light not yet delivered. It's like the universe is still writing its poem, and you're just getting the early verses. So the next time you glance up and see the faint smear of a nebula in the sky, maybe with a telescope, maybe just from a long exposure photo, know this: you're looking at a cradle. One full of sleeping giants. All right, sleepy traveler, brace yourself. We're leaving the cozy glow of the star nursery and diving into something a bit harsher. Because while starlight can whisper, it can also burn. And not the warm, golden kind of burn you get from a late afternoon sunbeam. No, this is high frequency, full throttle, skin-crisping ultraviolet radiation. That's right, tonight, you're drifting into the ultraviolet nightmares of the cosmos. Let's start with the basics. Ultraviolet, UV, light is just beyond the violet end of the visible spectrum. Your eyes can't detect it, but your skin definitely can. If you've ever gotten a sunburn after thinking, it's cloudy, I'll be fine, then you've had a close encounter with solar UV. And that's just from a midlife, medium-energy star like our sun. Hotter stars, those big blue-white O and B types, they crank out so much ultraviolet light they practically scream across space in wavelengths you'll never see. These stars are not friendly. They are massive, short-lived, high-energy furnaces that blast their surroundings with radiation. And what does that radiation do? It shreds things. Ultraviolet photons are energetic enough to ionize atoms, meaning they can knock electrons off, turning neutral atoms into charged particles. In regions near young, hot stars, UV radiation ionizes entire clouds of hydrogen, creating those colorful HII regions we talked about earlier. That glow you see in something like the Orion Nebula, that's hydrogen atoms recombining after being broken apart by UV rays. Now don't panic, but Earth would be utterly uninhabitable without our ozone layer, that precious smear of gas high up in the atmosphere that filters out the worst UV radiation. Without it, the sun's rays would fry DNA, blind eyes, and cook skin in minutes. Thanks to Starlight, you wear sunscreen. And fun fact, crocodile dung was once used as sunscreen in ancient Egypt. Yeah, historians still argue whether this was effective or just an early example of desperation. Either way, stars have been a threat to delicate human skin since long before Coppertone. Back in space, UV isn't just about danger, it's about discovery. Many telescopes are built specifically to detect ultraviolet light. Earth's atmosphere blocks most of it, thankfully, so these instruments need to be placed in space. One of the early UV missions was IUE, International Ultraviolet Explorer, launched in 1978. It helped us study stars, comets, and even the atmospheres of planets, all in the invisible ink of the cosmos. And then there's the GALEX mission, Galaxy Evolution Explorer. It scanned the sky in ultraviolet, revealing a side of the universe completely hidden from view. Hot, young stars glowed like embers on a black sheet, revealing where galaxies were forming stars at a furious pace. You could almost feel the heat through the data. UV light is also a forensic tool. When astronomers look at dying stars or white dwarfs, the UV glow tells us how hot their surfaces really are. Some white dwarfs blaze at over 100,000 Kelvin, too hot to emit much visible light, but they scream in UV. And what about supernova remnants? Those expanding shock waves from exploded stars send out ultraviolet radiation that illuminates the surrounding space, like cosmic crime scene tape. Astronomers use this light to study how energy is distributed, how dust is heated, and how space cleans itself up after a stellar demolition. Now, let's talk about one of the universe's most terrifying UV emitters, the quasar. Quasars are supermassive black holes actively gobbling matter at the centers of galaxies. As the matter spirals inward, it heats up and emits powerful radiation, including monstrous amounts of UV light. Some quasars are so bright they can outshine their entire host galaxy. You wouldn't want to live anywhere near one. The tanning booths on Quasar Prime must be devastating. Here's a fringe tidbit to roll around your sleepy mind. Some researchers speculate that early Mars might have lost its atmosphere due to relentless UV bombardment from the young sun. Without a protective magnetic field and ozone layer, the radiation stripped away its air, molecule by molecule. It's a planetary horror story told in invisible light. There's also a dreamy side to UV, believe it or not. Bioluminescent organisms on Earth often respond to UV. Certain minerals glow when hit with UV light. So when astronauts bring ultraviolet flashlights into lunar caves, or when rovers beam UV into Martian soil, they're not just probing chemistry. They're looking for signs of life that might have evolved to reflect, absorb, or emit in those wavelengths. Stars, of course, don't care about your sunscreen needs or atmospheric filters. They've been hurling UV radiation across the cosmos for billions of years. And when that light finally reaches us, most of it is blocked. But a tiny fraction, it makes it through. And sometimes it does strange things. There are even rare atmospheric events on Earth, sprites and elves, high-altitude lightning phenomena that briefly emit UV flashes. For a few milliseconds, the sky glows in colors your eyes can't detect, but UV cameras catch it. A hidden fireworks show just above the storm. Tonight, while you rest, the sky is filled with UV you'll never see, from stars you'll never meet, from galaxies that vanished eons ago. Their light, bent and filtered by time and distance, whispers through your window, And it's a good thing you can't see it all. Because if you could, it might just sizzle. But for now, it's quiet, you're safe. The ozone holds, the atmosphere protects. The UV light outside is mostly bounced, absorbed, muted to a gentle glow. What reaches you is soft, tamed by filters of air and water vapor. You lie there in the filtered starlight, not knowing that every breath you take is possible because ultraviolet light was not invited all the way in. Stars, as it turns out, are generous with their danger. And still, their light is beautiful. Things are getting warmer now, ironically, by slipping into the cooler part of the spectrum. You've spent time with the ultraviolet nightmares where starlight scorches and sears. But now we're tilting the dial the other way. Downshift. Slow burn. Welcome to the world of infrared astronomy, where the cosmos reveals itself not in blinding brilliance, but in soft, warm glows that drift quietly through the dark. Infrared light sits just beyond red in the electromagnetic spectrum. It's still light, just with longer wavelengths and less energy than what your eyes can detect. You feel it more than you see it, literally. The warmth on your skin from a sunbeam, that's mostly infrared. The gentle heat from a campfire's dying embers, same thing. Now imagine space is full of this glow. You just need the right eyes to see it. Infrared light is perfect for one crucial cosmic job, peering through dust. And not just cobwebs in the attic kind of dust, we're talking interstellar dust. Microscopic particles scattered through galaxies, nebulae, and star-forming regions that block visible light but let infrared pass through. That means if you want to see what's really going on inside a stellar nursery, or deep inside the core of a distant galaxy, you look in the infrared. That's exactly what the James Webb Space Telescope was built for. While its predecessor, Hubble, showed us the sharp, glittering structure of visible starlight, Webb sees the heat signatures of things hidden behind veils. Protostars still wrapped in dust clouds. Planets forming in the leftover disks of matter. Entire galaxies buried in the fog of cosmic adolescence. Webb doesn't just look further, it looks deeper. And the result's glorious. Remember those haunting images of the pillars of creation? Hubble showed you the dramatic outlines. Webb revealed the glowing cores inside, new stars still in utero, humming quietly in infrared. Infrared astronomy also uncovers cooler objects that don't shine in visible light at all, like brown dwarfs, those failed stars that never quite ignited fusion. Too big to be planets, too small to be stars, they glow faintly in infrared, like embers under cosmic ash. We might miss them with our eyes, but infrared telescopes catch them lounging in the dark. And then there are exoplanets, worlds orbiting distant stars, often invisible in visible light but easier to detect in infrared, where their faint heat gives them away. Some instruments can even analyze their atmospheres this way, picking up signs of water vapor, methane, or, if we ever get lucky, biosignatures. That's right. We could one day find hints of life not by seeing the life, but by sniffing the heat signature of its air. Historians still argue whether the first astronomers, those ancient skywatchers without infrared eyes, intuitively understood that there was more hidden in the darkness. Some cultures described stars that breathed behind the clouds. Others told of suns that never rose. Maybe they sensed something infrared cameras would later prove, that not all light can be seen. Let's not forget Earth-based infrared telescopes either. Many sit atop tall, dry mountains, places like Mauna Kea in Hawaii or the Atacama Desert in Chile, because water vapor in the atmosphere blocks a lot of infrared. You need high, dry, stable air to even have a chance. But even then, the Earth is warm, too warm. The planet itself glows in infrared, like a soft candle next to the telescope's sensors. That's why infrared instruments need to be chilled to near absolute zero, otherwise they drown in their own heat. It's like trying to take a photo of a firefly using a camera that's on fire. Not ideal. Here's a quirky tidbit. Infrared telescopes have accidentally caught astronaut footprints on the moon, still warm from human steps hours earlier. That's how sensitive this stuff is. One human footprint in the vacuum of space, visible only because the heat hadn't quite faded yet. Fringe speculation. There's been talk, faint theoretical murmurs, about using infrared to detect advanced alien civilizations. If a super-advanced species was producing tons of energy, it might leak as waste heat. That waste heat would glow in infrared. Some researchers even scan galaxies for infrared anomalies, odd glows that don't match what stars or dust should be doing. No confirmed ET sightings, of course, but you never know. In space, even heat leaves breadcrumbs. Infrared also lets us see galaxies in the early universe. Light from these galaxies left billions of years ago, but by the time it reaches us, it's been stretched by the expansion of space, shifted from visible into infrared. That's called cosmological redshift, and it means some of the oldest galaxies can only be seen in the infrared. So when we look through Webb's eyes, we're not just seeing heat, we're seeing time. The faint warmth of a galaxy that bloomed when the universe was still a toddler. And here it is now, brushing across your closed eyelids as you lie in the dark. Imagine ancient warmth, stretched thin by time, arriving tonight to meet your skin. And closer to home, infrared helps us monitor our own sun. It shows the temperature of sunspots, tracks solar flares, and watches the swirling dance of the solar corona. All of it glowing just outside the range of your vision, but not outside the reach of science. So now, as you drift deeper into stillness, picture this. The sky above is full of light you can't see, not because it isn't there, but because it's warm, not bright. It glows in hidden colors. It slips through dust. It curls around your fingers like fog you can't quite touch. The stars may shine in white and blue and gold. But their stories, their early chapters, their secrets, their silent songs, those live in the infrared. And tonight, those secrets are still arriving. Soft, slow, glowing. So far, the cosmos has been whispering to you soft colors, warm glows, light bent and filtered again. But now we're cranking the dial way up. Welcome to the realm of X-ray starlight. Here, the universe isn't gentle. It doesn't cradle or coddle. It blasts. It shrieks. It burns at millions of degrees and screams across the electromagnetic spectrum in bursts of radiation so powerful they'd sterilize entire planets if you got too close. Sleep well. X-rays are high-energy, short-wavelength photons. They're produced by the most extreme environments in the universe, places where atoms are stripped of their electrons, where matter moves near the speed of light, where gravity is crushing and magnetic fields are twisting space like taffy. In other words, the polite middle-aged stars from earlier, they don't hang out here. This is the hangout for neutron stars, black holes, supernova remnants, and galaxy centers that forgot how to behave. Let's start with one of the big players, the neutron star. After a massive star goes supernova, its core might collapse into a neutron star, a sphere just about 20 kilometers across, but with more mass than the sun. That's like taking Mount Everest and squashing it into a shot glass. The surface is a seething, ultra-dense crust where matter is crushed so tightly that atoms no longer have personal space. And it spins, sometimes dozens, even hundreds of times per second. Some neutron stars, called pulsars, emit beams of electromagnetic radiation, like lighthouse beacons sweeping through space. If Earth is in the path of that beam, we detect regular pulses of light, including X-rays. These X-ray pulsars are like ticking cosmic clocks, if your clocks could crush a spaceship and cook it from the inside just by being nearby. And if that neutron star is part of a binary system, well, now you've got drama. As it siphons matter from its companion star, the infalling gas spirals into an accretion disk, heating up from friction and gravitational compression until it glows in X-rays. These systems, called X-ray binaries, are some of the brightest objects in the X-ray sky. And then there are black holes. They don't emit light directly, of course. Nothing escapes a black hole, not even light. But like neutron stars, they feed. And when they do, the same process happens. Material falls in, spins up, and heats into a glowing, shrieking X-ray disk. Just before the point of no return, right on the edge of the event horizon, X-rays pour out in a last-ditch signal to the rest of the universe. Hey, something terrifying's happening here. Historians still argue whether early 20th century physicists imagined the universe could get this loud. When X-ray astronomy first launched in the 1960s, scientists were stunned to discover how active the sky really was. The night might look quiet to your sleepy eyes, but in X-rays, it's a battleground. Here's a quirky little historical nugget. The first cosmic X-ray source ever discovered was Scorpius X1 in 1962. At first, scientists didn't believe the data. It was too bright in X-rays, too intense. It turned out to be a neutron star feasting on gas from a companion star, a literal energy vampire glowing with invisible violence. But wait, there's more. Entire galaxies have X-ray personalities. At their centers, some host active galactic nuclei, supermassive black holes that aren't just quietly sipping gas, but slamming it down like a frat party at a gravity convention. These monsters emit X-rays as jets, disks, and blobs of hot plasma fly out from their cores. Some are so powerful they reshape the galaxy around them. All that, and you can't see them with your eyes. Only X-ray telescopes can catch them mid-screen. Speaking of telescopes, Earth's atmosphere does a great job protecting us from X-rays, which is comforting, yes, but it means X-ray astronomy has to happen above the atmosphere. So we send up satellites like Chandra, XMM Newton, and the newer NuSTAR, equipped with special mirrors that gently coax these high-energy photons into focus. X-ray optics are weird, by the way. You can't just use a regular mirror. The photons are too energetic. They'd blast right through or ricochet wildly. Instead, X-ray telescopes use grazing incidence optics, where the mirrors are angled so photons skim across the surface, kind of like skipping stones on a lake. It's clever and very expensive. And with these tools, we've seen some truly bizarre things. Like magnetars, a rare type of neutron star with a magnetic field so strong it could erase your credit cards from halfway across the solar system. Occasionally, they let out X-ray flares that are among the most energetic events we've ever measured. One blast in 2004 briefly altered Earth's ionosphere from 50,000 light-years away. Fringe theory alert. Some scientists have speculated that certain mysterious X-ray bursts, especially the irregular ones, might be caused by exotic objects we don't yet understand. Quark stars, strangelets, or even the hypothetical boson stars made entirely of force-carrying particles. No proof yet, but these high-energy regions are where all the weird stuff hides. And here, where it gets romantic. X-rays help us watch stars die, not just explode but fade. The afterglow of a supernova, the quiet cooling of a neutron star, the accretion wake of a dying binary system. X-rays show us the universe's hospice wing. Light that isn't trying to impress, just light that says, I'm still here, for now. Tonight, as you lie in the safe hush of your room, the X-ray sky is wide awake. Somewhere a black hole is feeding. Somewhere a dying star is whispering its final thermal sigh in a color you'll never see. Your body can't detect it. Your eyes won't twitch, but it's there. Tearing through space. Telling stories in screams. Not all light is gentle. Not all stars go quietly. And even in death they shine. SHHH, let's tune in. You've seen light that sears, light that warms, light that bends and twists and glows behind curtains of dust. But now, we step into a quieter wavelength, the longest, laziest, most mellow starlight in the universe. Radio waves. Yes, radio starlight, the kind that doesn't sparkle or shimmer, the kind you can't see or feel, but oh, the things it tells us. Radio waves are the turtles of the electromagnetic spectrum. Long wavelength, low energy, slow and steady. They don't burn like X-rays or pierce like UV. They wash, they roll, they pass right through dust, gas, and even entire clouds without a fuss. If the universe were a concert, radio waves would be the baseline. You don't always notice them, but they're always there, vibrating quietly in the background. Astronomers love them, because in the radio, the cosmos opens up in a whole new way. The first person to accidentally tune in to Radio Starlight was a guy named Carl Jansky, back in the 1930s. He was an engineer working for Bell Labs, trying to track down sources of static on transatlantic telephone lines. What he found instead was a repeating hiss that rose and fell every 24 hours. The culprit, the center of the Milky Way galaxy. Historians still argue whether he fully grasped the significance of what he discovered, but that faint, rhythmic hum became the spark of radio astronomy. Today, we build massive dishes just to listen to what Jansky heard. Not static, not noise, starlight stretched into sound. Not literal sound, of course. Radio waves are still light. They just happen to be in a frequency range we also use for communication. That overlap is both hilarious and useful. Somewhere between the frequencies of Wi-Fi and walkie-talkies, the universe is talking. And what does it say? Let's start with pulsars again, those spinning neutron stars we met in the X-ray section. Many of them also emit radio beams, and when those beams sweep past Earth, we hear them as precise, regular pulses. Some spin hundreds of times per second. They're so consistent, they make atomic clocks jealous. In fact, pulsars are so reliable that astronomers have proposed using them as galactic GPS beacons. If we ever build spacecraft to leave the solar system, we could navigate by pulsar. Imagine that, lost in interstellar space, and you pull out a map that says, "You are here. Next pulsar in 1.3 light years." Some scientists even carved pulsar maps onto the plaques sent aboard the Voyager spacecraft, hoping that if someone, or something, ever finds our tiny golden records, they'll know exactly where to return them. Now, Radio Starlight isn't just about navigation. It reveals things no other light can show. Like cold hydrogen gas, the raw material of stars. Hydrogen emits radio waves at a very specific frequency, 1.42 gigahertz. That's the famous 21-centimeter line. It's weak, but it's everywhere. By mapping this frequency, astronomers can trace the structure of galaxies, measure their rotation, and even detect gas in deep intergalactic space. The coolest part, you can literally listen to hydrogen. Scientists have translated the radio signals into audio, turning invisible waves into eerie cosmic music. It's not a perfect translation, of course. Space doesn't make sound in a vacuum, but it gives you a vibe. And that vibe is strange, peaceful, like a whale song filtered through a dream. Quirky fact, some observatories, like the massive Arecibo dish before it collapsed, were not just listening. They were broadcasting. In 1974, astronomers sent out the Arecibo message, a binary-coded radio signal beamed toward a star cluster 25,000 light-years away. It contained info about Earth, humanity, our DNA, and a cheerful diagram of a person with questionable proportions. Fringe theory time. A few researchers have speculated that fast radio bursts, FRB, those bizarre, ultra-brief flashes of radio energy detected from distant galaxies, could be artificial. Like maybe they're generated by alien tech, giant beacons, star-powered propulsion, laser communication. The idea is speculative, sure, but FRBs remain weird. Some repeat, some don't. Some come from ancient galaxies. One even came from our own galaxy near a magnetar. Still, most FRBs probably have natural causes, but they remind us that radio space is active, not silent. Just because it doesn't flash doesn't mean it's asleep. Then there are radio galaxies, huge structures that emit powerful jets of radio energy, often from the cores of galaxies where supermassive black holes are eating up matter and belching out energy. These jets can stretch for millions of light years, visible only in radio waves. Galaxies screaming into the dark, while to your eyes they look like faint fuzzballs. Some of the largest structures ever observed in the universe were found this way. And what about the cosmic microwave background? That's just stretched out starlight. Radiation from the early universe cooled and stretched into long, lazy radio waves over 13.8 billion years. The sky glows with it. You're bathed in it right now. Turn an old TV to a dead channel and a tiny fraction of that static. That's the echo of the Big Bang, the oldest starlight in existence. Let that settle into your pillow. You are, at this moment, blanketed in ancient, invisible light that has been traveling since long before Earth formed, and only radio telescopes can see it. Back on Earth, places like the Very Large Array in New Mexico or the Square Kilometer Array being built in Australia and South Africa are built to catch these gentle waves. Wide open dishes, silent fields, machines listening to whispers from space. Radio astronomy has its quirks too. Observatories need to avoid interference from human-made signals. Cell towers, microwave ovens, satellites. Some locations even enforce radio silence zones where cell phones are banned and microwave popcorn is an offense against science. So yes, in a way, the cosmos and your kitchen appliance are fighting over the same frequencies. Tonight, as you lie still and the fan hums softly in the background, know this. There are stars whose light you'll never see, but whose voices, long and slow, are still arriving. Somewhere, a pulsar ticks like a galactic heartbeat. Somewhere, a black hole's accretion disk hisses in static. And somewhere, Earth's quiet ears are turned upward, listening. Radio starlight doesn't dazzle, it doesn't sparkle. It endures. And while you sleep, the universe keeps talking. You've heard the crackle of distant radio stars. You felt the heat of infrared light brushing softly against the edges of thought. But now, the story of starlight shifts again, not toward stars as they are, but toward stars as they host. Because stars aren't always alone in their light. Sometimes starlight hides a secret. A world, maybe dozens, maybe just one. Orbiting, waiting, reflecting. Tonight, you drift quietly through the realm of alien suns and familiar light. For most of human history, we only knew one kind of star system, ours. One star, 8 planets, a few dozen moons, some rings, a healthy collection of rocks and ice. The solar system was our only lens for imagining what starlight could do. And then everything changed. In 1995, astronomers announced the first confirmed detection of a planet orbiting a sun-like star. 51 Pegasi b, a gas giant, bigger than Jupiter, hugging its star so tightly it completed an orbit every 4 days. Not quite Earth 2, but proof that planets were out there. It opened the floodgates. Now, thanks to missions like Kepler, TESS, and a few incredibly patient scientists, we've cataloged over 5,000 exoplanets. And the light that revealed them, it came from their stars. Because planets are sneaky, too small, too dim, you can't just see them easily, but you can detect their fingerprints in starlight. The trick is knowing where and how to look. One method is transit photometry. You stare at a star long and hard and wait for it to dim just a little. That dip in brightness means a planet has passed in front, blocking a fraction of the light. Do it enough times and you get a pattern, a period, an orbit. From just that tiny blink, you can calculate the planet's size, distance, and even atmospheric composition, if you're clever with your spectroscopy. Yes, we're still breaking starlight into its ingredients. Only now, we're doing it while a planet's atmosphere filters that light. Certain molecules like water vapor, carbon dioxide, or methane leave distinct marks. In the future, we may even find biosignatures, chemical hints that life, or at least biology, might be shaping a planet's air. Then there's the radial velocity method, measuring the Doppler wobble of a star caused by an orbiting planet. The star moves just slightly, a gentle gravitational tug, and its light shifts. Blue, then red, then blue again. From that wobble, we infer the planet's mass, its gravity, its hidden influence. And in some rare cases, we catch the planet directly, a pinprick of light next to the blinding glare of its sun, visible only because of clever instruments like coronagraphs and starshades. But even then, it's the reflected starlight we're seeing. A planet is only as visible as the light it borrows. All this means we now view stars as more than isolated points. We ask, what orbits you? What dances in your glow? What hides in your shadow? The next step is understanding where life might live. Enter the habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold. Just the right distance from a star for liquid water to exist. This depends on the star's temperature, brightness, and age. Around red dwarfs, the habitable zone is much closer. Around hot, blue stars, it's pushed far out. But proximity isn't everything. Red dwarfs, for example, are prone to violent flares, erupting with UV and X-rays that could sterilize a planet's surface. Historians still argue whether red dwarf systems could support stable climates over billions of years. Some say yes. Others think any hope of habitability would depend on thick atmospheres or magnetic fields to act as shields. Still, many of the Earth-sized planets we've found live around these dim, ancient stars. They may not be the warmest suns, but they last trillions of years, patient hosts, plenty of time for biology to evolve, if it can. Here's a delightful thought. The light from a planet's surface, even if we can't see it directly, might someday be inferred. Reflected starlight can tell us if there are oceans, deserts, even plant life. Some researchers hope to detect the red edge, a slight spectral signal caused by photosynthesis in plants. On Earth, it's clear. Could alien vegetation leave a similar mark? Fringe theory. Some suggest that advanced civilizations might engineer their planet's atmospheres to be visible on purpose, like cosmic billboards, artificial spectral lines, or even synchronized blinking. We haven't seen anything like that yet, but the idea has shaped some of the more creative SETI strategies, looking for out-of-place starlight. So far, we haven't found life, but we've found conditions, and starlight continues to be our messenger. Consider TRAPPIST-1, a tiny red dwarf just 39 light-years away. It hosts 7 rocky planets, 3 in the habitable zone. We can't see them directly, but we've watched the star's light dip 7 different ways, 7 rhythms, 7 shadows, and in each shadow, a world. Or take Proxima Centauri b, orbiting the closest star to the Sun, just 4 light-years away. It sits in the habitable zone. It receives a dose of starlight not so different from Earth's. We don't know if it has oceans or air or life, but we're watching, always watching. You, tucked into the softness of night, are surrounded by this quiet surveillance. We are the species that watches starlight for signs of someone else watching us, and all we need to do is wait. Because the stars don't hide things forever. Their light carries more than heat. It carries the shape of their families. Some starlight carries the rhythm of planetary motion. Some carries the signature of alien air. Some perhaps carries company. And someday we'll read it clearly. You've followed starlight across every color of the spectrum, watched it bend, stretch, whisper, and flare. But now we're going to talk about the light that's not there. Because for all its brilliance, the universe is missing most of its glow. Welcome to the missing light mystery, the frustrating, fascinating realization that what we see in the cosmos is only a small sliver of what's really out there. Starlight, for all its reach, doesn't tell the full story. In fact, it barely tells the prologue. Let's start with a simple observation. When astronomers look at galaxies, swirling, luminous islands of stars, they can measure how fast they're spinning. And from those rotation speeds, they calculate how much mass the galaxy must have to hold itself together. It's a bit like watching a carousel spin, and estimating how strong the center pole needs to be to keep the horses from flying off. But here's the kicker. When they add up all the visible matter, the stars, the gas, the dust, it doesn't add up, not even close. Galaxies are spinning too fast. They should tear themselves apart, but they don't. Something else, something invisible, is holding them together. That something is what we call dark matter. It doesn't emit light, it doesn't reflect it, it doesn't absorb it. Starlight passes through it like it isn't there. And yet, its gravity is unmistakable. It holds galaxies in place. It bends light through gravitational lensing. It sculpts the web-like structure of the universe itself. Historians still argue whether the earliest signs of dark matter, noticed by Fritz Zwicky in the 1930s, were taken seriously at the time. He observed that galaxy clusters had way too much gravitational binding for the amount of visible light they contained. He dubbed it Dunkelmaterei and was mostly ignored. Until decades later, when Vera Rubin measured the rotation curves of galaxies and proved that stars at the edges weren't slowing down as expected. They were whipping around at nearly the same speed as those near the center, something only explainable if a massive halo of invisible matter was surrounding the galaxy. Dark matter everywhere, silent, undetectable by light, but still there. And it's not just a small oversight. Around 85% of the matter in the universe is dark. That means all the stars, all the planets, all the glowing nebulae and supernovae, the entire electromagnetic spectrum, only shows you about 15% of the real stuff. It's like trying to understand a city by looking only at the streetlights at night. You see the glow, but not the buildings, not the people, not the dark, silent mass that holds it all together. The search for dark matter has become one of the great quests of modern science. Physicists have proposed all kinds of candidates: WIMPs, weakly interacting massive particles, axions, sterile neutrinos, even primordial black holes. So far, no direct detection. We see its effects, but the particles themselves remain elusive. Some fringe thinkers have even suggested modifying the laws of gravity, proposing that maybe the problem isn't missing matter, but our misunderstanding of how gravity behaves on large scales. These MOND, modified Newtonian dynamics theories, tweak the math to match what we see. They work in some cases, but not all. The debate continues. Meanwhile, dark matter keeps doing its job. It's the silent scaffolding of the universe. It shaped the first galaxies. It dictates how clusters form and evolve. Even the cosmic microwave background, the afterglow of the Big Bang, shows subtle imprints of dark matter's gravitational fingerprint. And yet, you'll never see it. Not directly, not through any starlight. Because starlight only tells part of the truth. There's another mystery too, a deeper one that makes dark matter look downright cozy by comparison. It's called dark energy. In the late 1990s, two teams of astronomers were studying Type Ia supernovae. Remember those reliable exploding stars from Section 10? They expected to find evidence that the expansion of the universe was slowing down over time, pulled back by gravity. Instead, they found the opposite. The universe was accelerating. The galaxies weren't just drifting apart. They were speeding up, as if some unknown force was pushing space outward, an anti-gravity of sorts, a repulsive pressure baked into the fabric of reality. This mysterious force, responsible for nearly 70% of the energy in the universe, is called dark energy. And just like dark matter, we can't see it, can't detect it through starlight, but its fingerprints are everywhere, in the structure of the universe, in the distribution of galaxies, in the silent expansion that stretches every photon over time. So let's tally it up. 5% of the universe is ordinary matter, the kind that glows, reflects, absorbs, the kind that makes stars, planets, people, pillows. Percent is dark matter, seen only through gravity. Percent is dark energy, seen only through cosmic acceleration. That means 95% of the universe doesn't shine, doesn't flicker, doesn't twinkle or blaze or beam. And starlight, the very thing you've been following all this time, is just the surface. It's the foam on the ocean, the firefly in the canyon, the tip of a vast, dark iceberg. But don't despair, because even though starlight doesn't show you everything, it shows you enough to ask the right questions, to build telescopes, to write equations, to whisper toward the void and listen carefully for the silence between the flickers. Every missing photon is a clue, every unexplained shadow is a map, and starlight, while incomplete, is still the messenger. A quiet reminder that the universe keeps most of its secrets in the dark. But you're one of the few creatures who even knows to look. And so we arrive at the final stretch, the long, glowing goodbye. By now, you've followed starlight from its violent birth in the hearts of stars, through dusty nurseries, ultraviolet tempests, and radio wave whispers. You've seen it bent by gravity, stolen by black holes, and used as a tool to detect distant planets and invisible matter. And yet, for all its drama, starlight ends its journey not in some flashy supernova, but in you. You lie there now, maybe still, maybe blinking slowly, your mind floating somewhere between wakefulness and dream. And somewhere at the edge of your vision, a photon arrives. A single packet of energy, born perhaps 1 billion years ago, maybe from a red dwarf in Andromeda, maybe from a supernova in a dwarf galaxy you've never heard of, maybe even from a dying star that no longer exists. It's traveled across the void, past asteroids and comets, through clouds of hydrogen. It's dodged gravitational pulls, slipped through magnetic fields, coasted silently through the expanding folds of the universe. It hasn't rested, it hasn't aged, it hasn't slowed. And now, it hits your retina. A rod cell catches it, a tiny electrical signal is triggered, your optic nerve responds, your brain whispers, star. The journey ends not in a telescope or a sensor array, but in a thought, a fleeting recognition. You don't even realize it happened. But it did. Starlight survives everything to reach you. You're part of its story now, the final chapter in a journey that began long before your species, your planet, or your star existed. It's easy to forget that you are fundamentally made of the very same elements forged in stars. Carbon, oxygen, calcium, iron, all synthesized in stellar cores or scattered in the aftermath of explosions. When astronomer Carl Sagan said, "We are made of star stuff," he wasn't being poetic. He was being painfully, gloriously literal. The atoms in your body were once starlight, compressed into fusion, shattered by gravity, flung across space, swept up into clouds, folded into earth, into plants, into animals, into you. You are light that became matter that became conscious. And now that same starlight reaches you again, not to create you, but to remind you of your origin, of your place, of your participation in a story so vast, so old, so quiet that it can only be told in photons. Historians still argue whether ancient humans understood this connection, whether they felt it when they watched the Milky Way overhead, unspoiled by city lights. Maybe they didn't know about redshift or hydrogen lines, but they knew something mattered up there, something old, something that made them small and important at the same time. And today, with all our science and equations and telescopes, we've circled back to that same awe. Because when you strip it all away, strip away the data, the spectra, the measurements, the diagrams, starlight is still and always will be a story. One that starts in fire, travels in silence, and ends in a glance, a sigh, a thought. Some light has been traveling for billions of years just to reach you tonight, and most of it will go unnoticed. It will land on sidewalks, on clouds, on rooftops, on satellite dishes and forgotten parking lots. But a tiny fraction will reach someone like you, lying still, listening, watching, wondering. And in that moment, you are not separate from the cosmos. You are participating. You are not just looking at the stars. You are receiving them. So the next time you see a star, just one point in the night sky, remember this. Its light is older than anything you've touched. Its journey was improbable. Its arrival miraculous. And for a brief moment, in the hush between heartbeats, you are the place where starlight ends. Or maybe where it begins again.